and share, no, and make the big screen. So the good thing about 9 a.m. when you're teaching online is that you don't have to go through all the traffic to reach the Skulltech. So 9 out of the sudden 9 is not too early. So I hope you feel the same. And yeah, and actually, like, teaching online has its own beauties and advantages. The only difference, the only kind of weird thing is when we have a lab, like a computing lab, then most likely it will be pure silence, and it feels really weird when nobody speaks and you're just alone programming something. And I cannot come to your laptop and kind of stand behind your back and look what you're doing. So this is kind of feels a bit weird, but yeah, but we'll get through this. I would prefer to teach, of course, to see all of you and have a bit more conversations with you, but like, life is life, so we have to do it online. But yeah, what I really like is interaction. So guys, feel free, ask questions, make comments. I really like that, and I will constantly ask questions to you, and hopefully you enjoy this course. Okay, so let's go ahead. So some course logistics. So we have Mondays and Thursdays, I believe, from 9 to 12. And this is, both sessions are typically lectures and practical sessions, but this is a lab course. So mostly you will program yourself, and I urge all of you to do this inside the given time, especially those who kind of have already high level of knowledge of Python. Still try to make all the assignments, because especially in the beginning it will be a boot camp for, like, in Python, but we will use all the exercises that we will do today and on Thursday later on to do parallel programming. So typically it will be 1 hour material and then followed by programming lab, or less than 1 hour, or maybe a bit more, but typically just like 1 hour material, some lectures, some stories, some like philosophy of programming, and then you do the programming lab. So the activity the activity type is the following: is first class participation 10%. Most likely we will just do the snapshot of the users who are in Zoom. I know we cannot check what you're doing, like you may kind of turn on Zoom and then go sleep, but yeah, try to stop by at least. Then homework assignments 30%, computer labs 30%, and sometimes they will be intertwined, because like we will start something during the lab and then it will continue as your homework assignment. So some of the, basically you can think of it as homework assignment is 60%. So you can take all the assignments, do it at home, and then just present them and defend them. And then final project will be 30%. Final project is so I bet you most of you will have questions about this. Final project is a project that uses Python and that optimizes Python code using the materials of the lecture or some other tools. Of course, we cannot touch every library that exists for Python, but final project has to be in Python, has to use some sort of parallel programming, some sort of code optimization, and probably the best idea is to do the final project on something that you're interested in, or something that you think will be your research topic for your like Skulltech life. So something like this. So what some textbooks that I recommend is the textbook called High Performance Python, and it's written by these guys, Misha Garelik and Ian Oswald. And right now in April, there was a second edition. So first edition, you definitely can find PDF online, but second edition is a bit better. And if you have a chance to somehow grab it, please grab it. And other resources, of course, I highly recommend Stack Overflow, and I hope all of you know this website. You can ask questions, get so basically this is a knowledge database for programming related topics. And then medium.com, Coursera, there are, like, of course you can find a lot of online courses, and Udacity and YouTube. If on YouTube you type in like Python courses, you'll get myriads of courses, and of course it's pretty tough to choose the correct one. So of course you can find all the topics that will be presented in this lab online, but it's kind of a collection of topics that I personally like and I think are relevant, and you have a chance to kind of do the practical work. So somebody already did the eating for you, and I'm just digesting the materials. Okay, so let's see. So we have a chat here. You can ask questions there, or you can stop me anytime. Feel free to stop me. I'll hear if somebody like has the microphone. We'll see how it works, because this is the first time I'm teaching so many people online. So I'm not sure how it will work, but you can try. We can try to kind of just use the microphone. And right. So let's continue. So some course prerequisites are the following. So it's best that you have laptop with installed Python, and it's preferably that you have, at least you have access to Linux or Unix based system. So I can probably help you with installations and with like library paths and whatever on Linux or Unix based machine, but I have no idea how Windows works, and I haven't used Windows for like more than 20 years. So those who have Windows, unfortunately you are on your own. But the good thing, you can install a virtual machine, a virtual box, and then install Linux there. Or at least you should have SSH client, because you will get access to Jaurès cluster, and then you can do the Python coding there. Then basic knowledge of Python is necessary. So at least you have to understand the basic types of Python, like dictionary sets and lists, and have some idea about list comprehension, and preferably some NumPy, SciPy, and Matplotlib. Yeah, knowledge. So prerequisite is also great mood and smiles, of course. So you have to have fun while learning, and then preferably you have already knowledge of Unix type systems, so you know how to work in terminal, you know how to get your way around the machine, like finding the contents of directory, changing directory, copying files, removing files, and so forth. Then preferably you already have a deep knowledge of Python and knowledge of C, C++. C++ will be only a small portion, like a very small portion. We will have some discussion about CUDA and programming on GPUs, but in principle we can get around without C and C++. Then knowledge of Jupyter Notebook, and this is a typo because the system changed it. This like Jupyter Notebook, NumPy, SciPy, Matplotlib, and you already have them installed. Otherwise, as I mentioned in the Telegram chat, you can use Google Colab, and then Google Colab offers already like the interactive interface to Python. And in fact, as far as I remember, they also have access to graphic cards. So I believe you are fine with this course using Google Colab, but I also urge you to try to use the Jaurès cluster, because from the survey I can see that most of you haven't ever worked on the supercomputer. So this is a good chance for you to get also this knowledge of how supercomputer works, and how you can use queues and you correctly use the supercomputer. And then preferably you have the basic undergrad level mathematics. So you know calculus, you know linear algebra, you know ordinary differential equations and partial differential equations. So, but we can also, but I believe all the homework assignments will be without differential equations, or at least some very simple differential equations. Right, so maybe somebody can drop a link. So drop a link to the Telegram into the chat, so that people can, those of people who haven't used or are not yet in Telegram can join Telegram channel. By the way, you guys have to decide together, like kind of self-organize and decide what are we using for communication. So I'm fine with anything. We can use Telegram, and I've seen you can pin messages to Telegram. I don't know how to do it, but maybe someone of you can pin messages. We can try to use Slack, and this will be a bit more easy to track different homeworks, for example. So we can use Canvas. It's up to you. So please self-organize all together and give me a kind of a joint decision. Okay. Let me check also the Telegram. Can I? I'll quickly check. Somebody joined the old high performance Python group.
Can you please link Telegram in Zoom chat?
Yeah, how do I do it? I'm not good in many computer topics. I just copy the what? I don't know. Guys, can somebody do it please for me? Yeah, there it is. Thanks, guys. Yeah, I don't know where those links are. I'm kind of mastodon in terms of new technologies. Good. And yeah. Okay. Right. So also on the canvas, it's a bit outdated list of topics. So we will have the following list of topics. Oh, okay. Approximate list of topics. So this might change depending on our pace and depending on maybe some of the topics are too easy for you. So you all say like, hey, let's kind of continue without it. But roughly our topics are the following. So today is an introduction, logistics, and then we have a crash course on Python. So I'll give you the assignments immediately after like short lecture notes. I'll give you some assignments and you will program them and yeah, and then those assignments we will use later for optimization. Then we will have next time we will have crash course on Python will be continued. So I will add another assignment, and then we will have a crash course on using supercomputers, so Linux and how to log into supercomputer and how to work there and how to use queues and where to find your compilers, your Python, and then so forth. Then third, we will discuss briefly the computer architecture, so different types of processors and why, like what is a thread, what is a process, and what is parallel programming, how you can describe parallel programming in, let's say, in real world examples. And then we will start with code profiling, and then next we'll classify parallel algorithms, discuss Python multithreading, discuss Python multiprocessing and Jupyter parallel, and maybe we will already start on lecture number 4. We will start discussing distributed systems. So lecture number 5 is distributed systems. This means a cluster of computers. So right now all of you have laptops and maybe desktops, and all your desktops and laptops already have a processor that has several cores. So you, so since 2005, you cannot, as a good programmer, you cannot live without some sort of parallel programming, either multi-threading. So if you want to be a good software engineer, you have to know multi-threading at least. But now imagine you have those laptops connected into the network of computers, like 10,000 of laptops connected between each other. And of course, this becomes a distributed system. You have to, the only way right now for general programming is to send messages through the network between the computers. And this can be done low level through like TCP/IP protocol using sockets library in C, for example, or this can be done using higher level APIs, for example, MPI. This is message passing interface. And yeah, we will learn that. And there is a wrapper around MPI in Python called MPI for Pi, and we will use it. So we will spend 2 lectures on that, and we will learn quite a lot about MPI, quite a lot of advanced topics. Then we will continue with graphic cards. we will discuss CUDA, PyCUDA, and QPy. So yeah, so you will learn how to use graphic cards. Then number 8 will be just-in-time compilation and accelerating Python with Numba. So Numba is exactly this framework for just-in-time compilation. So you now Python is not compiler language, right? So it's interpreted language, but you can compile several portions of it and make them fast. So we will touch that. Then we will have a lecture about visualization in Python, so different ideas, especially 3D visualization in Python, because matplotlib is a great library, but 3D capabilities are not its strongest suit. Then we will do Cython and PyBind. So these are the kind of the idea, the methods how to write C-like code, or PyBind. Actually, you write a C++ code and then you create a library for Python. And then 11, 12, this is under question marks, because this depends on you guys and maybe some of you who are doing especially deep learning and data processing. You can prepare these lectures yourself and teach them in this class, and this can be treated as a final project. And also 12 is we will discuss different libraries. So briefly discuss different libraries for code optimization and for parallel programming, and also discuss other languages like JAX and Julia. And this is also someone of you can do it as a final project, kind of read about these languages and different libraries, understand them, prepare examples, prepare a small laboratory, like kind of small examples that students can do during the lab, and then present it. And this can be treated as your final project, so you can get 30% of the mark for that. And then we will have last part of our course is you will defend your project. Yeah, and later on we will discuss the project, but the earlier you pick your project and start working on that, is the better. Because I can tell you, last year there were guys who tried to do visualization last night, and of course last night libraries couldn't, like, there were problems with installation, so basically guys had only 1 hour of project, and yeah, this looked not very great. So try to do the project, start doing it slowly, and use more time for it. Okay, so like I'll roughly present myself. So my name is Sergey Rykovanov. I'm right now associate professor in CDI Skoltech. So I graduated from Lomonosov Moscow State University in physics faculty. So I'm actually trained as a theoretical physicist. But then after graduating from Moscow State University, I did a lot of computational physics and a lot of high performance computing in plasma physics. So I did my PhD in Germany in Ludwig Maximilians University in Munich from 2006 to 2009. And then I stayed there for another couple of years afterwards as a postdoc. And then I moved to Berkeley, to Lawrence Berkeley National Laboratory, and did my postdoc there. So there I worked on particle accelerators and gamma sources, and also a lot of computations and and a lot of computations on graphic cards. So back then I realized that a lot of things are so much faster on graphic cards, and we had access to like most recent graphic cards, and especially it was an experimental machine back then, so nobody knew how to use graphic cards, so those guys who were programming on graphic cards had the machine almost for themselves, and it was great. So you had no waiting time, just submit the job and then it runs. It was great. And then in 2014 I moved back to Germany. I got a really good offer from Helmholtz Institute Jena and a lot of funding, and then I was for almost 5 years a group leader there. And then since July 2018 I'm in Skoltech, so I'm, like, one can say I'm pretty new. So what that a bit more than 2 years. So what do I do in Skoltech? I'm the head of the high performance computing and big data lab, and this was actually established a couple of weeks ago, so it's very fresh. So now we have a dedicated lab for high performance computing, and one of the most powerful Russia supercomputers is part of this lab, and all the amazing technical engineers who make this machine run, who are basically the heart of this machine. They're also part of the lab. And I'm also the leader of the HPC track within the CDICE program. So I try to assemble all the courses, so all the, how's that called? Curriculum for the HPC track. And yeah, so, and the thing here is we have to kind of tweak a bit, knowing what kind of specialists we have in CDICE. So, and depending on that, we choose the courses. And also I'm instructor for high performance computing and modern architectures. So this is the course. I don't know how many of you took this course already. This is the course in term 4, and I'm also instructor for this high performance Python lab, which is free credits, and also I'm doing parallel computing and mathematical modeling and data intensive applications. So quite a lot of teaching. Yeah. Then our usual and all like course teaching assistant, and this who is always here to help, is Rishad Zagidurin. He's a PhD student in our lab, and great guy, great specialist. So I believe you will, when you have to pick whom to defend your homework assignments. And it was funny last time that like there was a huge queue to Rishad, and like nobody went to me, to myself, although I'm also kind of not a very bad not a very bad teacher, so I'm not super strict. But anyway, Rishad did his bachelor in Higher School of Economics from 2012 to 2016. Actually, he did a bachelor in what's that, political science, so it's quite weird. So Rishad did political science, and then he thought, okay, enough of political science, I want to do computer science. And then he entered like Russia's, one of Russia's most powerful universities in computer science department. So passed all the mathematical tests, everything. And he finished, graduated from Moscow State University in computer science department. And then from 2019, he's a he's a PhD student in my group. And in Skoltech, he's a TA basically for all the courses that we teach. So he's already, probably he can teach all those courses without me, and I can be his teaching assistant. So anyway, he's teaching assistant for all the courses like high performance computing and high performance Python lab and parallel computing in mathematical modeling and data intensive applications. Rishad, you here?
Yeah, hi.
Good. Good morning.
Yeah, hi, Sergey.
Good. So, all right. So what are the goals of the course? Is first, not to be afraid of programming and Python, and overall, not to be afraid of supercomputers, because like I was afraid of supercomputers. You know, when you see the picture of the supercomputer, it's like some sort of huge machine, and then if you listen to it, there is a lot of noise coming from the cooling, and it looks crazy, like all those blinking lights, and then you don't know what to do with it. But it's actually not so it's not so scary. And in fact, on one of the courses, we teach how to build a supercomputer out of virtual machines, and students have like 6 hours, 3 to 6 hours to assemble a supercomputer from scratch, and they do it. And then you have a supercomputer with all the software installed, all the queues installed, and all them, like you can install monitoring and everything, and you have a working version of a supercomputer. So another goal is to be able to write parallel programs on modern multi-core CPUs and GPUs. So as I mentioned, if you want to be a good software engineer, you have to know parallel programming in one way or another, because all your processors, all the modern processors are multi-core, or like inside their architecture are some ideas like vector programming, like GPUs are vector machines or vector type machines because they're a bit different architecture. So you have to know this and basically learn how to use large computing infrastructure, meaning that we will have a like a crash course on how to use the supercomputer, and you will be able to log in, copy data to the supercomputer and off the supercomputer and work on it. And of course, have fun learning. So we will have, I tried to assemble various examples that are pretty cool, like from mathematics, from like what we will. I will probably give you an example of like studying the time series based on the stocks, and then you can try to write your own trading bot, or try to predict the price of, I don't know, Apple for the next 1 month, and then using your recommendation, we can all invest or sell Apple and get, I don't know, get rich. And yeah, and the final goal is also that you finish with a really cool project and you have fun doing it, and the project that involves Python code optimization. Okay, any questions about logistics and about what about waitlist? Will we be assigned to the course also project? Yeah, waitlist. This see, the problem is 50 people is already a lot, because I also have problems finding teaching assistants, and like going through all the assignments myself and with Rishad, who is also not officially the teaching assistant. It will be very tough. So waiting list, I believe there is like 100 people, so it will be very tough for me. And unless we find like 4 teaching assistants, then it will be problematic with the waitlist. But you have to check with the education. So I'm not here. I'm not the guy who kind of decides all the education level questions, right? And but you can join definitely as a free listener. You can join as a free listener, right? Final project. If it is, we can discuss it. If it's a very simple project, like, I don't know, take the take the Maxwell's equations and parallelize them, then one person can do it. If it's a more involved project, I don't know, you can try to do reinforcement learning on like some game, but you can do it yourself, not just downloading OpenAI library, but kind of do something yourself, or do the neural network from scratch yourself, or do distributed deep learning from scratch, like using, let's say you use TensorFlow, but you write all the necessary procedures for message passing yourself. Then it's a bit more involved project, then like 2 people can do it. So this depends on the project. Okay, so if it's a more involved project, you can do it in groups. But if it is kind of a simple project, I don't know, visualize game of life in a crazy way, create a YouTube video about this, then one person can do it. But for example, last time what we had a 3-dimensional game of life. So this was 1-person project. We had actually, I don't remember right now very clearly what happened last year. Rishad, do you remember some cool project?
I was trying to think as well, and for some reason it's unclear to me also. I remember like there were 2 guys trying to visualize Julia said in 3 dimensions, but like that project wasn't very successful. Yeah. There were also a group of 3 people who tried to do some, not reinforcement learning, but some sort of learning on Atari game where you play ping pong, and I think that's it. At least that's all I remember.
Yeah, or the final project, you can really write the trading bot, or like analyze the you take all the stocks from Moscow Stock Exchange, try to find correlations between the between the stock prices. I'm sorry. And or you can predict the series and then present it, or use the neural network for prediction, some kind of this. This can be a project. Okay, any questions on this? But we can discuss it also during the lab session. You can come up with the idea of what you like to do, and then we can discuss the project. Okay, so if no questions, then let's continue. Yeah, so first comes the general introduction. I'll talk a bit about high performance computing in general, high performance in Skoltech. Why is it necessary? Why do we have to take care about this? And I will briefly introduce Jaurès cluster. This is kind of, it's not related to Python, but as I seen from the surveys, not a lot of people used supercomputers. So you have to kind of get an idea why we need supercomputers, where do we use them, and why is it necessary to learn this at this stage. So, and I would like to start with this very nice sentence or very nice logo, which was in one of the data communities. It was the logo, and then I find it really great. It's to outcompete is to outcompute. And indeed, in our age, in our era of digital era, it's indeed so. So imagine you have like exponentially growing size of data. Data is not structured, right? So it's not anymore your typical databases, like table-based structured databases, meaning that you have a table, one row, one column represents, I don't know, people, names, second column represents their age, third column represents their height, and so forth. So no, right now we have sounds, like videos, images, and to generate and to process this data is another level of computing demands, right? So, and then it will grow, continue growing exponentially. Nothing will stop this. Of course, most of this data is rubbish. If you go to any internet forum or internet website or TikTok or whatever, like Pokemon Go, you understand like what I'm saying. So most of the data is rubbish, but there are these gems in data that can propel us as a humanity forward. So what our goals as a humanity is, of course, like really global goals is to get away from Earth and like start colonizing different planets, and then go away from solar system, start colonizing other stars, because we have limited lifetime for our planet, for our star. So if we think like really globally as a humanity, we must kind of go away from Earth. So I don't know, people from Space Center, do they agree or not agree, or is it some kind of crazy thoughts? But anyway, high performance computing provides competitive advantage for industrial and business companies and research groups. Some examples. For example, PayPal, they bought back, I don't remember, 10 years ago, they bought a supercomputer for, I don't remember the price, but let's say $1 million. And then, no, maybe $100 million. So something like this. And then they used this supercomputer for spam filtering. Oh, no, not spam filtering. For kind of spam filtering, for finding out the fraudulent transactions. So finding out which transactions are bad. And of course, you can do it. Those are guys who do deep learning. You understand that you can do spam filtering or this fraudulent transaction filtering using neural networks. So you can use the supercomputers to do this. And then, so they spent $100 million and they saved $1 billion. So this is immediate calculation of the profit they had using the supercomputer. In principle, you must understand, especially in Russia, it's really hard to calculate the benefit of your supercomputer. And I believe there is one guy in the audience who studied economics, right? Ilya, you're here?
Yeah, I am here.
Okay, good. So yeah, I remember you from the entrance interviews. So yeah, so you can think about this, how you can calculate the benefit of the supercomputer, especially in Russia, because Russia is a bit like special in a good way as well. So how can we also calculate the benefit of your laptop? So you spend like $1,000 for it, and like what did you earn using it? So it's really hard to calculate, but sometimes it's easy. For example, as an example, for PayPal, it was easy to say, okay, we spent 100 million, we saved 1 billion. Other examples, rendering, of course, rendering of animations, 3D animations. People use the technique so-called ray tracing, right? So if you have an object, for example, a mouse, a Mickey Mouse is an object inside your program, and it has certain texture, like fur and eyes have certain texture. So ray of light going through the eye, it will get reflected, so you will have nice blinks in the eyes, and the fur will absorb the light, and the fur will be kind of dark, and so forth. So, and all this requires a lot of computation. So rendering is also a huge part of supercomputing business. And for example, Disney uses this. And the funny thing is Disney hired a couple of my friends because they did plasma physics, and because they did doing plasma physics, they did particle simulations, and then Disney basically hired them to do rendering and to speed up rendering. Other examples, well, you can find a lot in the internet. So this couple of examples already show that HPC is very important, and it's also used in oil and gas. In fact, right, oil and gas. How do they do the study where to drill? So imagine you stand as an engineer or as an owner of the oil company, you stand in front of the desert and you know there is oil somewhere. And then the question is, where do you drill? And of course, what they do is they do seismic analysis first. So they send acoustic waves downwards through the core, through the soil, and then they measure what comes backwards, and then they try to create a model of the reservoir of the soil, right? And then this takes a lot of computation time. In fact, most powerful industrial supercomputer is owned by the oil and gas company in Italy called Eni. So also hugely used in oil and gas. Also in Russia, if you look at the list of most powerful supercomputers, you'll see that oil and gas is very important. Then digital pharma is prominent user, and the story here is that developing one new drug takes 10 years at least, and takes up to $1 billion. So because you have to go through different stages, testing stages and so forth. Artificial intelligence, as I mentioned, data is growing. So I believe most of you used single graphic card so far, but imagine your data set is so huge that if you use one graphic card, you wait 1 year, and then probably your data set is already outdated. Or your model can be huge that it doesn't fit to the graphic card, and then you have to use supercomputers, so different graphic cards. Aerospace and research, of course. So, by the way, what is high performance computing? Like, what do you think? So, any ideas? What is high performance computing?
Maybe it is when we try to find the optimal solution of some problem with the minimal.
Okay, any other ideas? Well, it's part of HPC. Kind of what you're saying is optimizing the codes. It's part of the HPC, but like more general, what is high performance computing? How do you guys understand it?
Maybe the main idea is to compute everything at high speeds, and this is the main goal.
Okay, we're getting to more. Okay, so
maybe to use everything that we have to fully exploit every component the hardware has to offer, or every resource that we can use.
Mm-hmm. This is part of HPC. This is part of HPC, of course. Knowing your architecture is important, but this is not the HPC itself. HPC itself is kind of a more abstract term. So speed is also important, and then like making codes that run super fast is also important. But in general, do I have it here? Yeah. So we will understand it as basically simple as aggregation of power well beyond your typical laptop. So you know the speed of your laptop, or you can calculate it knowing your like gigahertz of your processor, knowing everything. So your laptop is performs roughly like tens of 10 to the 9 operations per second. This is called operation per second. Is called ops, and typically it's floating point, so it's called flops, floating point operation per second. And your laptop typically does 10 to the 9 or 10 to the 10, maybe 10 to the 11 operations per second. And modern supercomputers do almost 1 exaflop. Exaflop is 10 to the 18, so they do five orders of magnitude more. And aggregation of such power is what we will call HPC. So very abstract so far, right? But let me go to the next slide. So, and high performance computing is not only programming, and it's everything. It has to be holistic. So you as a team really working on HPC, you have to do different things. First, you go from the bottom layer. Bottom layer is infrastructure. It's data center infrastructure. So you have to know how to cool your systems, because right now if you look at the graphic cards and the modern era graphic cards, like this small piece of hardware produces up to, or eats up to 500 watts of power, right? And produces heat. And now if you can imagine one rack like this, right? And you have to put servers there. And how many servers can you put is limited, because you cannot take heat away. Actually, the most money is spent not on electricity, it's spent on cooling. So imagine you bought your computer, and out of the sudden you don't have a room where to put it. It's actually, right now, this is the case in Skoltech. We are still building the data center. And there are different ideas how to cool this. So because air cooling, so you can just put it like your normal laptop in the air, and then it create a fan, and then that will blow air, cold air, for example. And this is already not enough. So you have to use liquid cooling or some other ideas. So data center infrastructure is extremely important. Then software, hardware infrastructure. So how your server is built. Like you have your server with 4 super nice graphic cards, and then you put very slow processor, or processor that doesn't have enough bus lines for data transfer. And out of the sudden, you don't have a very nice architecture. And then although you have all those graphic cards, but your processor is not tuned nicely to the other architecture, and your hardware doesn't work efficiently. Or you created a very stupid like interconnect, and out of this you don't get so you haven't done your homework right as an architect, as a supercomputer architect. You haven't done your job correctly, and then the supercomputer is not working efficiently. So this, knowing your hardware, knowing the peculiarities of all the hardware, knowing why the GPUs are this way, why the CPUs are this way, what's the difference between the Intel CPU and ARM CPU, and so forth. It's also very important. And of course, you created your data center, you created your supercomputer, but then you don't have enough knowledge of software. Also bad, because, and I'm speaking about supercomputer software, like what runs the supercomputer, like your operating system. So you typically you wouldn't use Ubuntu on it, or you wouldn't use Windows on it, or you wouldn't use Mac OS for supercomputer, because you don't want like any graphic interface running on it. So, and then you have to you have to tune all your drivers. Imagine you have 10,000 of servers, and if you want them to work in parallel, they all have to have the same system, right? So you have to put the same system on 10,000 nodes, and you can imagine like this is not very trivial how to do it. So you definitely don't do it by hand. And then you have to introduce the queue system. So you don't want people to start their jobs like from the command line or from the Jupyter notebook, and then 100 people start their super nice deep learning simulation on one node, and then out of the sudden nobody gets anything because you're concurrently running your job. So of course you need a queuing system, and this is the job of system administrators to tune this. So, and this layer is super important, and most of the people like forget about this. And of course, next level is a bit higher level, is what you do with it in terms of you create mathematical model. For example, your neural network is a mathematical model, right? It's a bunch of matrices, and the way they connect to each other, or graphs, or your model for the physics, for example, for water. You create a model, right? And then you create equations, you create kind of discretized equations, and so forth. And then computing architecture and methods. What I mean here is, given the graphic card, you have to know that it has certain limitations and certain advantages. And knowing this, you accordingly create your numerical method, right? So for example, matrix multiplication, great on graphic cards. Matrix by vector multiplication, great on the graphic card. But if you have some kind of particle simulation where particles have to interact, and you have to distribute them on the grid, well, then you have some questions if the graphic card will be correct. So you have to know how to tune your numerical methods to computing architecture. So this is the kind of the more higher level. And of course, the upper level is what is your goal. You have to have a goal. Like, I want to create image processing tool that will, looking at the X-rays, find like cancer or something like this, right? So medical applications, for example. And in our course, we will touch only this, but this is, I'm just saying this, that high performance computing is not only parallel computing, it's not only like creating numerical methods, and it's not only learning how to use matrix multiplication. It's all those things together. And of course, to create a team of people that do this is extremely tough. So imagine right now we have what, like 1 month of lab and then 2 years of working here, and creation of this whole infrastructure is extremely demanding. And so when speaking about HPC, always remember that it's not only like mathematics, it's not only linear algebra, it's not only deep learning. Okay, so right, and the lab was established in 2010, and so just as a strategic like kind of investment. And what we want to do, we aim pretty high, so we want to be #1 place. So when students speak about HPC, we want them to speak about Skoltech. So you guys are here also to help us do that by returning the feedback. So we always ask to return the constructive feedback. Like from last year, we implemented already all the feedback, or most of the feedback, into this course. And right, we want to be like first to second, like top 3, maybe Russian supercomputer lab in merit of scientific and industrial output, and maybe also in terms of power. So right now we have a computer that's #8, and we aim to create like all the projects and all the project that will run and then demand more computing power, and we want to reach like top 3 in Russia. So right now what we have is the supercomputer, which is called Jores, after Jores Alferov. It is a special computer. It was first in Russia to be designed for artificial intelligence. So back then in 2017, when it was designed, like late 2017, all the computers were more or less general purpose, and specialists in CDICE, they decided to, like, knowing that CDICE is mostly about deep learning, about data processing and mathematical modeling, to create a computer that's tuned for artificial intelligence. So it's a very energy efficient machine. It has only 74 compute nodes, so it's not much. So essentially it's 74 servers. From those, 26 have powerful graphic cards. So each node has 4 NVIDIA Tesla V100, which have NVLink. So NVLink is the very fast interconnect between the graphic cards. And then these graphic cards, they have tensor cores. Tensor cores is a special architecture that does matrix multiplication, essentially. And matrix multiplications is a driver for deep learning, right? So those tensor cores, they ideally suit the machine learning applications. And this machine is very energy efficient. So only 90 kilowatt of electricity consumption. So you can imagine your kettle or iron that you use or washing machine uses roughly 1 kilowatt. So, and this is only 90 kilowatt, but 1 petaflop of computational power, which is quite a lot if you think about this. And we almost made it to the top 500 list. So top 500 list of most powerful supercomputers in the world. We were a bit late, but we will get there eventually. So we have also quite a meager, actually, not a lot of storage system. We have only 0.5 petabytes of storage system. This is actually the bottleneck right now, so that we are almost out of space, as always, as you know from your own laptops. There is no garbage collector. So if I look in my downloads folder, all I downloaded, all the text files, all the PDFs are still there, so I have to clean it. But right now it's #8 actually, so there's a bit outdated, but it's #8 in Russia. So it's a huge success for us, and you can imagine that Skoltech has the machine that's top 10 in Russia. And it was installed by our team, our technical team. So yeah, all the assembly, all the cabling, all the installation of software. So it was done by our system engineers. Yeah. And just some numbers. So already in 2020, we have scientific papers that cite Jores around 40. This is a really good number, including 4 Nature Index papers. So Jores enabled about $1 million research grants. So people do, when they do research grants and they need the computing time, they of course apply for the computing time on Jores, and then they did this research grants worth of $1 million, which is also a very, very nice, very good number. So there were 5 master theses and PhD theses accomplished. And this year it will be, of course, much more. Number will grow significantly. There were about 40 articles about JORES and research performed on JORES. There were 2 hackathons done on JORES and approximately 100 total projects and more than 200 total users. And JORES is a critical tool for CDICE researchers, is a tool for grant generators, and we have a dedicated HPC team. And this is also really important. So that hardware is one thing, but of course, if you don't have people, educated, high-level people that can run this hardware, then of course your supercomputer is also not useful. So that's actually the difference when we speak about, let's say, cloud and your dedicated supercomputer. Cloud might be even cheaper, but you don't have the same level of support. And if something is not running correctly, well, you wait quite a lot of time. But here you have people that know what they're doing, and then they can help you much faster. Okay, so I'll distribute this slide. I will not go through all the topics, but this is the list of topics that we do in our lab. So we have actually 2 professors that are running the lab. It's myself and Professor Nikolai Koshev. So I'm mostly doing, so I prefer doing myself like photonics and plasma physics, so kind of mathematical modeling, fluid dynamics. And for example, Nikolai Koshev's group is doing, for example, neurointerfaces and inverse problems in geophysics. And then we also have numerical and computational methods and supercomputer infrastructure research. So guys, if you're looking for research projects, let's talk. Unfortunately, the number of students that can enter the lab is limited due to the regulations, but yeah, we still have some places, so we can talk about this. I'll distribute this slide so later on you can look at the list of topics. Right, and
can I ask?
Yeah.
What is meant by neurointerfaces?
Yeah, this is basically what they're trying to do is they have magnetic, so encephalography and magnetic encephalography. So you have, you put detectors on your head, and then you try to measure what kind of electric currents are inside the brain. And then from those brains, those signals, you want to learn how the brain works. So I don't know if you guys looked at the Neuralink presentation by Elon Musk. I think it's more marketing than real science, unfortunately. And of course, if you look at the scientific results that were done before Neuralink, and you find a lot more and a lot of interesting things. Like people use electrical encephalography, magnetic encephalography to measure the signals inside the brain. And yeah, basically this group does exactly that. So if you're interested, there are a bunch of projects, because measuring is one thing, but making use of these signals is another thing. So you need a lot of computing for this. You need to solve the so-called inverse problem, right? So you know the signal, but you don't know the distribution of your dipoles, right? And then you have to generate the distribution of dipoles that produces exactly the same signal, right? So this is inverse problem. So if you guys are interested, please write to Nikolai Koshev. He is also looking for students. Right, name using thousands of. Yeah, this was previously okay. Where does the name JORES come from? Yeah, Rishad mentioned correctly. It's named after Jores Alferov. Jores Alferov is a Nobel laureate, and the reason is the following. Jores Alferov got his Nobel Prize for semiconductor heterostructures. What is the heterostructure? Those of you who did physics, is basically you create a material where you have two wells, 2 potential wells, and they have different height, different properties. And then by doing this, you can create, for example, you can, well, from these heterostructures, you can create lasers. You can create solar batteries. In fact, using exactly these results from Jores Alferov, Russian space station, Soviet space station used solar batteries. And of course, if you use these heterostructures for lasers, then you have to think or I ask some of you guys, how does the interconnect between the between the computer nodes work? What technology does it use? Or the cable that comes to your house most likely has this technology. The cable, the internet cable that brings you internet most likely has this kind of technology. What is this? Any ideas?
It might be also a variation of some optical fiber.
Yeah, it's fiber optics. Exactly, fiber optics. You're right. It's fiber optics. Well, what sends the signals? Like fiber optics, essentially, optics means there is some sort of signal going. It's not visible light, but it's infrared. It's 1.5 microns. But somebody has to create this signal, right? Modulated signal. You basically modulate your light, and then demodulator will read it and find the information. And this is done by the semiconductor laser. And the semiconductor laser is again comes from the Nobel Prize of Jaurès Alférov. So essentially, all supercomputers in the world use Nobel Prize from Jaurès Alférov. Our computer as well. So that's why we have our interconnect between the nodes that uses fiber optics and of course uses invention of Jaurès Alférov. So this is one of the reasons we called our supercomputer Jaurès Alférov. And yeah, Jaurès Alférov was also head of the scientific council of Skolkovo. And we presented the computer to him, also presented the symbolic keys, and he was very happy to kind of to give his name to the computer. Yeah, so I hope this answers. Okay, let's continue. Right, so let's have a 5 minutes time. I'll drink some coffee, and then those of you who haven't done it yet, please fill out the survey. And you also will need an account for Jaurès, so please fill out, those of you who do not have the account on Jaurès sandbox cluster, please fill out the form, this kind of form. So you can please also copy these links to the Telegram, and let's have 5 minutes to fill this out. So let's continue in 10 hours, 10 minutes. We continue. And meanwhile, I'm here, you can ask questions.
Can you send the link in the chat of the Zoom, please?
Yeah, sorry, of course. Just a second. First of all, Telegram, and here. And survey, hold on a second. This is one, and the second is here.
I have a question for the sandbox account creation.
Yeah.
So I already filled this out for the introduction to Linux and supercomputers.
Then you don't have to do it. Then you don't.
Okay, yeah.
Yeah. You need only one account. So those of you who already have account, or those of you who who are attending Sergei Matveyev's course, Introduction to Linux and Supercomputers, you don't have to fill it twice. Yeah, Irfan, thanks. Well, I have a kid. I have a kid, so so she wakes me up early, so and then she brings me happiness every day. So that's why I'm always energized.
Yeah, it's great to know.
Thanks. Yeah, I hope my strategy is that you enjoy the course and have fun. Roland, you still in Garching?
No, actually, I moved back to Vienna, but it's not any better here, so
Yeah,
also
yeah,
still
yeah.
very early.
Oh, nice, nice, nice. You have a lockdown in Vienna or not?
Not yet, but I think it's only mere weeks or days before it eventually happens. Let's see.
Okay. So guys, can you like write where you're now, like just for fun, like who is outside of Moscow? It's interesting to see where you are. I'm in Moscow. I'm not interesting. I know Rishat is in.
You forgot the name?
Rishat is in Nabережные Челны, yes.
Yeah, that's right.
Chengdu, China. Chengdu, which province is that? Beijing. Taliati, cool. Sichuan, oh, Sichuan. Very, I tried Sichuan food. It's very spicy. Very spicy. Taliati, good. Novosibirsk. Good. So you're lucky, the lucky one, because 9 + 4 is what? 13. Chengdu.
Can you show again the slides with the possible research topics?
Sure. There. You see them or not?
Yeah, I see them. Thank you.
Екатерина, Новосибирск, Академгородок or Новосибирск?
No, just usual Novosibirsk.
Okay. But studied in university or?
I studied in NSTU, so it's
Okay.
also Novosibirsk.
Тольятти and Набережные Челны. We have representatives of our car making industry.
Machine industry, yeah, I was thinking the same thing.
Okay, actually, okay. So we can start. Let me check the survey. It's very interesting, and then I can maybe share the results with you as well. 35 responses, good. So it was anonymous, so I can share. Okay, so we have mostly people from CDI, so mostly first-year master students, mostly CDIs and space, CDMM, energy, and life sciences. Okay. Mostly, I guess, mostly machine learning, robotics, high performance computing. Time series. So you will create the trading bot for us, make us all rich. Deep learning, physics, cool. X-ray. Oh, this is actually also inverse problems, a lot of inverse problems. So, and this can be done on the graphic card. 38 responses. Cool. Nice. Cancer genomics, cool. Business applications, nice. And most of you are at 7. So there is this kind of distribution. Okay, 40. Okay, there are more and more coming. Okay, but there is a distribution, so that's good. So today we have a Python Python bootcamp, and then we continue next session. C is more like this. Okay. And most of you haven't worked with supercomputers. Good, so you have a chance to work with supercomputers. And yeah, that's good. So guys, finish, like you can continue working on this a bit later. So let's continue with the lectures. So, right. So briefly about Python. I guess if most of you are treat yourself as 7 in Python, then you know it. But let's briefly go for it. And then, so what is Python? Python is an interpreted, object-oriented, high-level programming language with dynamic semantics, and it has high-level data structures. And yeah, you can read it from like this. There is a part that has essays, python.org. You find essays on Python, and yeah, it's interpreted, free, and so forth. Interpreted means that you don't need a compiler. You just type in, and then on the fly you can work. Object-oriented, you can use object-oriented paradigm, create classes, create inheritance, create complex data structures together with methods, but you don't have to. You can write your code as you want. And in fact, later on we will use the very non-Pythonic way of writing codes for acceleration of the code, which sounds weird. So because in NumPy, for example, you have matrix multiplication. So you don't write your for loops to do matrix multiplication. You call matmul. But we will use actually this matrix example for speeding up the code. And we will write the very stupid way, like different for loops, like 3 for loops for matrix multiplications. Like you wouldn't do that if you were a Python programmer, but if you were a C programmer, you would do it. And we will see how to speed this up. High level means that you don't need to care about anything. So everything is abstracted. Everything is abstracted away from how machine interprets and executes the code, which is both good and bad, of course. And we will discuss why is it bad. It has dynamic semantics. You can change meaning on the fly. So for example, you can say A is a string, like hello, and then the next line you can say A equals 5, and then it changes, completely changes the type. It's built in for most of the Linux and Unix-based systems, not on the Windows, I believe, but it's a built-in language. So my computer already came in with Python. And if you install Ubuntu or Linux, you already have Python there. And it has a large collection of libraries. You can do almost anything. You can watch YouTube videos. You can download YouTube videos. You can, I don't know, download files. You can go through the website, like parse the website, and so forth. You can send emails. You can send SMS. You can call using Python. You can analyze sounds. You can generate sounds and like crazy amounts of things. Almost everything. You can write computer games on Python. Yeah, it was developed by Guido van Possum in 1989 and developed in the early 90s. The name comes not from the snake, but from the Monty Python Flying Circus. And those who haven't watched it, try to watch it. It's amazing humor back from 70s. And Guido is not involved so much in the development anymore, but he's the so-called benevolent dictator for life. So he continues to oversee Python's development. And he recently, I believe this year, he quit or just retired from Dropbox. So he like his most recent workplace was Dropbox. And it was open source development from the start. And it relies on large community input and third-party add-on software. I believe if you go to GitHub, you see how many libraries are there, and TensorFlow is a third-party library. TensorFlow, I believe, is developed by Google. PyTorch is developed by Facebook. What else? There is for distributed learning, there is the library called Horovod. It's developed by Uber, and so forth. And yeah, OpenAI, company OpenAI, they have a lot of like AIGM or something like this. So a lot of libraries you can find. So there were different versions, 2.0. Well, of course, it started with 1.0, then 2.6, 2.7, and then version 3.0 appeared in 2008, and it was not backward compatible, but the previous code is easily converted or migrated to 3.0. I had this problem of converting actually because, for example, one of the like changes that I noticed is they changed print. Print used to be without brackets, and out of the sudden it became a pure function. So that now you have to pass that string to the print, and I had to change all the prints in all the codes, and I had quite a lot of prints. And the reason I had a lot of prints is that this is the way I debug the codes. The best way to debug the code is to put the print statement inside it and then look for it if it appeared or not. Of course, actually, yeah, I still use it. Although you have a lot of debuggers, but I still use the good old print debugger. Right, and the latest stable version actually just appeared is 3.9, and they have really cool features. Maybe we will have time to speak about this. They now have, I believe now they have pure multi-threading. Igor, are you here? Is it from this version they have?
Yes, hello. I suppose it's available from version 3.8.
Okay, okay. So, but now they also.
Yeah, it was announced a bit a year ago, maybe later.
Okay. So those of you who know Python, you know that, especially C Python, that it has global interpreter lock, GIL. So because it's an interpreted language, and the problem is you cannot really do multi-threading, although the multi-threading library exists, but it's not multi-threading. It's actually concurrent, like in terms of it's you don't really create multiple threads and run them in parallel. So that's a bit problematic, but yeah, so since 3.8, there is an option to do it. It's not a very safe option, but you can still do it. So what are the alternatives? Of course, C, C++, Fortran. We use it in our lab, and back end of all your deep learning software, of data processing software, is written on C and C++, like TensorFlow backend is C, C++, PyTorch backend is C, C++, because PyTorch actually first, I believe, was pure torch, and then there was PyTorch, right? So, but of course, NumPy also is not written in Python. The backend is C, and SciPy is C, or scikit-learn, those of you who use it, is also C. And pros, of course, of these languages is they have great performance, and most of the scientific codes are written in these languages. And you have to imagine about, especially when talking about science, we have, since the beginning of the computing era, we have what, 30 plus 20, 50 plus years of development. And like you can imagine how many human hours was spent on developing computing codes, testing them, like implementing different physics inside. And then you cannot really change like from these codes because there is a lot of knowledge inside, and rewriting them from scratch is, yeah, it's a bit problematic. Then the cons, of course, is syntax is not optimized, at least not yet. I believe like C++ already has like new versions, new standards have a lot of things implemented, like I believe like lean space and things like that. But it's not the same as in Python, of course, and it's not causal programming. So you cannot just sit down like and, well, unless you're a pro, you cannot sit down and program like anything you want. There is no interaction mainly, so you compile and then you run, and then you compile and then you run, and then difficult visualization. So you have to know your way around like libraries like OpenGL or maybe some higher level libraries, but you have to implement them inside your code and for visualization. Difficult text processing generally. So I remember when I started learning C, I had to write the text parser on my own. You have to imagine how many lines of code is that, like to parse text in C. Oh, that's terrible. But yeah, it works anyway. So, and then alternatives are mathematical, Maple, MATLAB, and IDL. These kind of languages, they are of course interactive. They provide great visualization. They have extensive libraries, but of course they cost a lot. They are proprietary, and most likely they are unpleasant for large-scale programs and non-mathematical tasks. Okay, so why Python? Python is free, and it's interactive. It's extremely readable. So if you look at the Python code from somebody else, most likely you will understand it. It's simple, so you can learn it from scratch within a couple of days. Actually, this is also what happened to me. I for my PhD, I was writing all the post-processing in MATLAB, and then the license went out, and then we didn't have more licenses. So, and I had, I believe, like a month left for my PhD, and I had to do something, and I learned Python within, what, 3 days. And it's, especially after MATLAB, it's super easy. What's next? Yeah, simple, great documentation, and total abstraction of memory management. And this is also a problem, of course, total abstraction of memory management. You don't know how the memory, unless you really dig into the details, you don't know how the memory works in Python. And I can tell you that memory for a single object is not that trivial. For example, integer, you can imagine, you can type in like 5, and this is the integer that holds, I believe, what, 64 bits? 8, or integer is how many? Anyway, this simple integer. You can type one.
Integer is not standardized.
Exactly. So simple integer, exactly. That's what I'm going to. It's not standardized because if you type 5 is 5, but you can also type 100 times 100 5s in a row, and it still will be integer. So now you can imagine C will not get it. C will not understand it. In C, integer is fixed length, right? And also the objects in Python are interconnected. So you have some like complicated graph memory structure. And yeah, so, and there is a garbage collector that does garbage collection for you, but typically your memory management in C and C++ is much better because you do it yourself. Object-oriented, but no, you don't have to, and you have rich built-in types and rich standard libraries, so you have already lists, sets, arrays, strings, dictionaries, and you can use them for your code. You have standard libraries for MATLAB-like arrays like NumPy and scientific algorithms like SciPy, and you can easily wrap existing C and C++ code in Python, and other way around. The other way around is probably more difficult, but it's also doable. It's amazingly scalable. So, and it's also great because, for example, when I develop a new numerical method, I don't write code in C. I first do it in Python because you can easily draw, like on the fly. You can create pictures. You can create like all the you can experiment with the coefficients and blah blah blah. So it's very interactive. So you can build small scripts. Also, I build scripts for running jobs on the supercomputer in Python. So very easy. I can spawn millions of tasks within one press of the button. Or you can write million lines projects like PyTorch, TensorFlow, and so forth. And you can use it like occasionally or full time. And if you look at the, let's say, Headhunter or like Monster or Indeed, like all the headhunting companies, and you look that a lot of people are looking for Python programmers. And you can really do whatever you want. And it's pretty simple. Typically, yeah. And typically, because the documentation is so great, even if you forgot something, you just type in like how to, like blah blah blah, do this and this, how to send messages from one node to another, and then you immediately have the working example. And very simple syntaxes is very comprehensive, then nothing, no problems to learn. And also what we will learn here is that you can have performance if you need it. So as an interpreted language, Python is of course slow, but that's why we are here. We want to speed it up. And of course, in the limit, Python goes to C. So C is pretty fast. If you do it correctly, of course. You can do terrible things in C. You can create memory leaks. You can do not optimal algorithms. But if you do everything optimally on C and Python, they converge, and Python, of course, converges from like slower side to faster side. And it's used widely: Dropbox, Spotify, YouTube, Google, Reddit, and so forth. And and maybe we can have a round of like, if you want to share your cool projects that you did in Python, maybe you can share, guys, like whoever wants to share. Ivan, I'll share the slides after the lecture, or during the bootcamp. I'll put them on the box and share the link. So slides are not yet there, but you haven't missed a lot. It's just basically random rants from myself about Python and life and meaning of life and things like that. So no materials so far. Like, yeah. Right. So guys, who wants to share some cool projects that you did in Python? Come on, Rishad, you start them. Oh, Igor, you start. You did recently a really cool project.
Well, the things I did was on C++, not Python, technically. So.
Yes, so I'm currently doing my research project under the supervision of Sergey. What I'm doing is it's a physical task of interaction of laser ultra short pulses. Ultra short means that it's 10 to the power of minus 18 seconds in duration. And I have to write the code which would count properties of incident field and reflected field. And the first task that was given to me by Sergey is to make this code faster. And what I did is I tried to find the slowest part of the code by some profiling. And after that, I decided that it is possible to accelerate this code without very much effort. So I used Numba library, and I used some of its properties to accelerate it. And actually, I got quite good speed up, so it was up to 5 times faster. And the most important thing for that acceleration was to set the input data types of the function and output types of the function. So when you use Numba, you have an option to write, for example, that if you use integer types as input, so you type it and the code becomes faster. And this so-called signature of the function, when I wrote it down, so it was a 3-dimensional array of floats as input and 3-dimensional array of floats as output. So when I typed it, it became really faster, and this was very convenient. So guys, don't forget about this option of Numba. It is very convenient because it requires just 3 to 5 lines of code without modifying existing code. If you write your projects on NumPy or on pure Python, they are optimizable by Numba. So that's I find it convenient.
Okay, thanks. So other guys, like especially from like not physics, data science, what are you doing, guys? Like deep learning, what are you doing? Or CLS, like genomics, what exactly are you doing? Or Space Center, what kind of projects It's very interesting, like for you to share, and let's interact a bit.
Hi, my name is Yerjan. I'm doing research related to processing of fMRI data. So it's like three-dimensional scans in time. So it's like 4 dimensions, and like if you want to apply deep learning methods, and like say, for example, now I'm trying to implement variational autoencoders to like extract some meaningful information out of it. So
you're using like PyTorch or what kind of?
Yes, PyTorch.
Okay, good, thanks. So anybody else? Robots, what are you doing with robots, guys?
Well, the mobile robotics lab developed a library that allows to like perform like matrix transformations related to how do you call it? Well, maybe someone from mobile robotics lab will help me now, because I know someone from there is here now.
Yeah, and actually from mobile robots, it's extremely important to have efficient code, because on board of the robot, you cannot have like a supercomputer, right? So on board of the robot, mobile robot, even like your cell phone is already a supercomputer. So, and the code has to be efficient because, yeah, because you have limited power resources. Okay. Okay. Well, you can later on, like we can talk also about your project. So, but I guess according to the distribution of Python level knowledge, you already have some experience with it. So now let's continue with bootcamp. So I have some project for you. So I will not. Maybe I'll create a separate breakout room for those who kind of lost in Python. So or looking at the. But these tasks will be lost, so I can create a different separate breakout room, and we will have a really short, brief introduction to Python. I will program something really simple and use matplotlib for plotting and for loops and linspace. And those of you, of course, who have done it already, you can proceed with the tasks. So we have actually not today and tomorrow, today and when next time, Thursday. So what we will practice is the following. You will create a bifurcation map. I will tell you what that is in a second. And fractals, Julia set, and Mandelbrot set, and then you will program shelling model. It's a type of cellular automata. I will also tell a bit later. And next time I will also introduce spectrogram and tell you more about what spectrogram is. And those who, especially those who do digital signal processing or done this course or will have this course, you will definitely need the understanding of spectrogram or wavelet and things like that. So we will go through this step by step. What kind of visualization tools we need? You of course you have many options, and if you Google, there are many interesting libraries that do visualization, and different libraries have different like color maps and look much nicer and provide you with interaction. So you can have like matplotlib plot which you can zoom in, zoom out, and like drag and so forth. So but generally we will use matplotlib, pyplot, maybe animation, and CM. I don't even remember what's that, to be honest. Maybe color, I don't know. Some other options are Seaborn and PyQt graph. But in this course, you're most likely fine with matplotlib, except for the lecture for visualization, where we'll have different things, different libraries for 3D visualization. So first task is the bifurcation map. Who has seen this before and know what
this is from House theory, no?
Well, it's not necessarily house theory, but yeah, well, this is called chaos. Well, actually not, this is not called chaos. I forgot, to be honest. It's from nonlinear dynamics, yes.
Yeah, I thought something similar. Oh, I saw something similar in terms of, yes, some equilibrium theory courses.
Mm-hmm. Yeah. So, right. What that is the following. Let me actually connect my, hold on a second, I'll connect my iPad, and then I can explain what that is. Zoom. Can anybody? Oops. Can somebody please tell me meeting ID and Rishad, can you look up the meeting ID?
Yeah, just give me a second.
Mm-hmm. 953 648 5 6 Ah, there is a password. Oh, how do I find the password? 9696. That's me. Great. So I'll stop sharing here, and then I'll share my iPad. Так, okay. So what is this map? So we had xn plus 1 is equal to xn. No, what was there? R xn 1 minus xn. So, and this comes from the biology, actually. It's, well, this is a model for the evolution of the population of fish in the pond. So you imagine you have a pond, and then fishes here. I'm not good at drawing, but this is a fish. This is fish. So kind of certain amount of fishes. And then you have also a certain amount, because it's a closed system, you have certain amount of food, and they can also replicate the fish, depending on the situation. If there are too many fishes, they don't replicate. If there is too many fishes and not enough food, then they die. So, and this is depend on this coefficient basically. And then one term is the growth. One term is the growth of the population, describes the growth of the population, and one term describes the decrease of the population. And now, depending on this parameter R, you will have different situations. And this is not this is a toy model, but last year people asked me, like many people asked me, why the hell are we doing this? And actually, you can find that in Norway, there is an institute that does exactly this model to model the population of cod. Cod is the fish, right? По-русски это треска. So cod, and the problem is, like we will see in this model, that depending on this parameter, if you kill too much fish, if you catch too much fish, the population will never be restored. Okay, and this is on the graph that I showed. Like you had this, let's say this is population, and this is time. And remember, there was like kind of this, or it can start from here and then slowly decline to 0, depending on the parameter. So now let's look at this mapping, right? This is a mapping of new x on the old x, right? So if we rewrite it, this is something like xn plus 1 equals r xn minus r xn squared, right? So this is what? This is a parabola, obviously. And what we plot here is the following. We plot the map of, here it's xn, and here is xn plus 1. And we plot also the line. By the way, this is done, this mapping is done for from 0 to 1. And we draw the line x equals x. So this is kind of the line where the mapping is exact, or like 1 to 1. So xn plus 1 equals xn. We will need this. And let's draw this parabola. So, and we have different options for parabola. For example, like obviously it has the peak at 0.5. So this is 1. This is 1. So the parabola looks like this, depending on the r, right? This is 0.5. And now, how do we find, like graphically, how do we find this this dynamics? So xn plus 1 equals this rxn minus rxn squared. So we start with a certain point. Let's say we start here, right? So this is our initial x. Then this means that in order to find xn plus 1, right, we go to the parabola. So this is our xn plus 1, right? Then we treat xn plus 1 as x again. So we go to this line again, right? So now this is our old x. And now to find the new x, we again go to the parabola, again go to the x, now go to the parabola, go to the x, parabola, x, and so forth. And you see in this case, the population got to the certain level, but which is not 0 and which is stable. So this depends, of course, on the height of this parabola. So this is, I believe, 0.25 r. And depending on, of course, on the parabola, we will have different situations. So let's say we have xn plus 1, parabola like this, and line like this. So we start somewhere here, go to the line, go to the parabola, line, line, parabola, line, and so forth. In this case, it will go to 0. So in this case, for certain r's, the population will be extinct at some point, right? Okay. So this is this mapping, and you can easily, of course, do it. So create a for loop and then see how it goes depending on r, and plot the evolution of x. And there are different regimes also. So far we found 2 regimes. One is extinct. One is goes to a certain value. And the thing is, for certain r's, you will have a really strange behavior. Your population will start jumping from year to year. Like it will at some point it will be, if you plot time and x, so it went here and then start jumping like this. And this will be called exactly the bifurcation. So at some point it will have 2 values. So 1 year it will have one value, another value, and then back to this and back to this. At some point it will have 4 values, and at some point it will have one value. So let me just stop sharing again and go back to the slides. Right, so how you do it? You pick your x0 randomly from 0 to 1, and r, you pick a value of r, and then you do this evolution for every r. And then you try to find which value does it converge to. Or if it doesn't converge, you just plot like last 100 of these steps. And then, so this is r, and you see if your r is less than 1.
Sorry, we don't see slides.
Sorry. Yeah. Let me share. Where is it? Here. Here. Right. So you pick your x0 randomly from 0 to 1, let's say. Well, probably not 0, but some you can pick a value. Let's say you pick 0.5 and stick with it. And then r you can change. And then for every r you plot this evolution and see to which value it converges. Or if it doesn't converge, you plot like last 100. And then you will see the following. So if r is less than 1, your population will definitely be extinct. And then depending on r, it will start growing, but still converge to 1 value. And at certain value of r, your population will jump from year to year between 1 value and another value. At some point, it will start jumping between 4, and so forth. And you will create this kind of picture. And this is called bifurcation map. And this is very useful. I later on shared a YouTube video with you where they describe why is it important, and also more cool stuff. So first task for you And so step-by-step guide you can read also here. I'll share the slides. If there is no questions about kind of mathematics behind it, so it's very interesting. If you're interested, you can find real physical systems that exhibit this kind of bifurcation. Okay, task 2 is the fractals. So you have to create this kind of picture or similar picture. It's very similar to what we discussed before, like this mapping xn plus 1 r xn 1 minus xn. But now you're dealing with the complex plane, right? So z can be complex, and now we have zn plus 1 equals zn squared plus c. And c is a constant that belongs to complex numbers. And depending on where you start, you will have different pictures, different sets of fractals. And you do exactly, you continue this progression and until you find that it doesn't converge, or if it starts exponentially blowing up, then you put like a black color. Right, a different example of Julia set. And in fact, if you put, I believe, C to 0, so you probably heard about Mandelbrot set, and Mandelbrot set is one of the Julia sets. And step-by-step guide is the following: you fix a value of C, and then you can implement the map and plot the evolution of Z. And then you plot, then you play around with the values of of C actually, and see how the evolution changes. Right. If for given z0, if the sequence converges, then you use black color. If it exponentially diverges, then you use white color. And if it starts jumping between n values, then you use different colors. And then you plot this Julia set, and I believe when c equals 0, this is called the Mandelbrot set. Now the question for you: so who has seen Mandelbrot sets before? Can you put a plus in the chat? Okay, so most of you have seen them. Now the question for you. So anyway, who hasn't seen them? This is a great chance for you to program it, and you will remember it for your whole life. This Mandelbrot. Do it once, and you will know what it is. And I'll send you the video, which is pretty cool, and then you will have a bit even more understanding. Unfortunately, this course, not unfortunately, but this course is not about nonlinear dynamics, so we will not dwell into the different systems and fractals and different nonlinear oscillators that exhibit this. But it's still a fun thing to do, and for your general education, it's extremely important. And fractals, in general, understanding what a fractal is, like a self-similar structure, is very important for your life. So, okay, now the question, kind of a fun question. So, Julia set is self-similar. It's a fractal. Mandelbrot set is also self-similar. It's a fractal, so it repeats itself, right? So if you zoom in, it's still the same structure. So, and the guy who invented the Mandelbrot set, in fact, his name is Benoit B. Mandelbrot. And I'll tell you first the story and then answer the question. In fact, he was working. He was a brilliant mathematician, and he was working back then in IBM, in the research division of IBM. And back then, they didn't even have the same level of displays. So in order to plot his fractals, he had to print them on the plotter and then go back from his desktop computer to the printing room, take the printouts, look at them, and then go back, change the parameters, go back, and so forth. So we are living in the amazing times where these fractals and these like theorems and deep learning is so easy for us, right? It's just one line for certain things, like create a model of convolutional neural networks like ResNet 50. Boom, it's done for you. You don't even have to think what's behind it, right? So, and back then he had to run for the printers. So anyway, what's your idea? What is B in Benoit B. Mandelbrot? If we are talking about fractals, then what is B?
It's a recursive acronym. So B means, once again, Benoit B. Mandelbrot.
So B means Benoit B. Mandelbrot. It's a fun, of course it's not the case, but it's just fun. It's like the same as in GNU, right? What is GNU?
GNU is not Unix.
GNU is not Unix, yeah. So it's kind of weird. Finished. Okay, anyway. So your second task is fractal. Just do this fractal. You can talk between each other. Please don't share the code, but you can discuss like how you got to certain points, like algorithmically. And task 3 is the shelling model. Shelling model is a cell automata. Cell automata is, for example, when you have a cell, like cells, a grid of cells, and simple rules. So suppose you have a two-dimensional grid. Like here, the two-dimensional grid made of cells, right? And each cell has 8 neighbors. So, and this map can be large. And let's go back to this task. So suppose you have 2 types of agents. You have X and 0. For example, X and 0, so black and white cells. Or so 2 populations of the 2 agent types are initially placed into random locations of a neighborhood represented by a grid. So you have your grid of cells, and you randomly put X's and zeros or black and white cells. And after placing all the agents on the grid, each cell is considered either to be occupied or empty. So for example, black cell can be considered to be occupied and white cell is empty. And now we must determine if each agent is satisfied with its current location. So a satisfied agent is one that is surrounded by at least a certain % of agents that are like itself. So for example, if the black cell is surrounded by a certain percentage of black cells, it stays. Like if 50% of the cells are black, then I stay. So if 50% of the population of these cells is occupied, then I stay. If not, I move. And the same with the white color. So white color, if the white cell looks, if around me is white colors, I stay. If not, then I move. And if the agent is not satisfied, it can be moved to any vacant location on the grid. And you can choose the new location by any algorithm. And you can, for example, a randomly selected cell may be chosen, or the agent could move to a nearest available location. And all dissatisfied agents must be moved in the same round. So, and after the round is complete, a new round begins. You again count your neighbors, you again count the not satisfied cells, and again move them. So again, this is a game with a simple rules, right? For every cell, you calculate the neighbors, and depending on the color of the neighbors, or on the amount of the neighbors with the same color, you move or not move or stay. Okay. Yeah, this is segregation. Eugene, you did it before, right? Or you just Googled for it? Yeah, this is Schelling model of segregation, exactly. It was back in 60s, I believe. And this model was described to find how if you initially start with random distribution of the city, why after certain points you have neighborhoods, right? Different neighborhoods. So, and how to deal with it, how to change it. Yeah. Right, so this is an amazing task actually, because later on think about how you parallelize it. And then when you parallelize it, this will be a task for like more motivated people, because parallelizing this task requires skills not only in parallel programming, but also understanding in statistics. We will talk about this later when we start parallelizing it, but this is an amazing task, and you can later play around with it, like add different agents, or add different houses with or empty cells and 2 types of houses and so forth. Right, so yeah, this is called the segregation model correctly, and map can be large, 100 by 100, or you can choose like 1000 by 1000 and so forth. And let's do periodic boundary conditions. Periodic boundary conditions means that for this guy here, right, all those 3 guys are neighbors. Periodic means that we glue this boundary with this boundary, and this boundary with this boundary. So essentially, we end up on the torus, right? So each household on the map has 8 neighbors, like 1, 2, 3, 4, 5, 6, 7, 8. And the agent decides to randomly move if less than R, and you can pick the number, are of the same color. So for example, if R is 0.5, then he calculates, okay, in this case, I have only three guys from the same color, so it's less than 0.5%, then I move. Here I have 1, 2, 3, 4, 5. It's more than 0.5, then I stay. Okay. Right. This is task free. This is cellular automata. And here are some steps. Like I share with you. These are just the steps for the lab work. We don't have to discuss it here. And that's it from the lecture material. So just start doing the tasks. Let me quickly save this. Export to PDF. So where do you prefer me to put this lecture? Like Telegram is probably not a good idea because this is quite large.
Canvas, upload it to Canvas.
Yeah, I'll upload this to Canvas, and you can start today, and we continue on Thursday. And again, even those guys who think or who put like 10 for Python or 9 for Python, of course, this for you will be easy. But of course, first of all, this is cool mathematics, which you will use later in your life. These are cool tasks, especially segregation model. Now you have a bit more understanding why cellular automata can be interesting. And fractals, you will also have an understanding what fractal is. And I believe also in neural networks, you use fractals, right? Sometimes. Yeah, I'll put it on Canvas. Some people don't have access to Canvas. Okay, let me put it to Box then. Just a second. I'll create a box and I'll share the public link. So new folder, which is called HPPL 2020. And later on, I'll put also the video of the lectures there. Meanwhile, you can ask questions. I'll stop sharing. And I cannot minimize Zoom. Okay, that's good. So I'll go back to the files. Save.
So we need to implement these tasks from scratch, right?
You can use libraries, but please don't please don't just copy the code from Git. Of course, this is a task that I will not tell you.
Okay.
But yeah, obviously some of these tasks were done by other people already. So, but the point is you learn something, and yeah, deadline is 2 weeks. No, of course not in 1 hour. So this is the link to the lecture. Please check it, and I also put it to Telegram. And please, somebody who knows how to do it, please. Please pin this message. Okay, so just jump into this. Can you guys put a plus if you want me to create a separate breakout room and show you some Python things, like simple Python things? Those who put more than 5 definitely don't know this already, like NumPy, linspaces, matplotlib, and so forth, Jupyter Notebook. So, but put pluses if you want me to create a separate breakout room and show you some Python things. Okay.
I have a question. Can I ask?
Sure.
So it is classwork plus homework, or it is only classwork and homework will be something else?
No, as I mentioned, we will not have a clear separation between lab works and homework. So you start with this, and later on, this will be part of your homework. So, for example, later on, we will have to parallelize this fractal. The fractal. Okay, so this will later become your homework. So that's why I say it's 2 weeks from now. But I urge you to sit during this time and work, because this is your time, and this this discipline will help you. Otherwise, the things will pile up. Okay. Good. I'll create a breakout room for everybody and who wants will join, and who will not want to join will not join. So I created a breakout room. I open it, and you guys who want to learn a bit of Python, like, please join. Everybody will receive an invitation. You don't have to join, okay? And I'll be there, so I'm available now on. So Rishat will be. Rishat, can you stay here? Igor, can you stay here?
Yeah, I'm gonna stay here.
And if you have questions, because I will not be here, then
I'll try to answer them. Okay, yeah, I get
it. Somebody is he not Guido van Possum?
Yeah, it's Guido van Rossum.
Ah, shit. You know what? This is this stupid keynote. I'm sorry. The keynote changes a lot of things. I'll have to stop this K9. Like, this is one of these funny moments. Okay, thanks. Can you post it somewhere? Can you post it to Telegram? It's funny. Thanks. Okay, I'll go to the room. Anyway, if questions arise, I'm on Telegram. Okay, 32 participants. Wow, 33. Okay, so I'll do some simple stuff. So guys, do you have Python installed already on your laptops?
Yes, Jupyter Lab.
Yes.
Jupyter Lab. Okay, that's good. I have Jupyter Notebook, but let me just Jupyter. So guys, can you put minus if you don't have Jupyter Notebook right now? Just a second. Just a second, I'll prepare something. Okay. Okay. Anyway, I'll show you something. Why is this? Hold on a second. Share screen and Firefox there. So here we have like the typical Jupyter Notebook interface. But those who don't have, let's see, Google Colab. You can go to Google Colab, and you can hear, it's in Russian, but you can hear there should be like create a notebook. You create a notebook. It takes some time, but in principle here you have again your typical IPython interface. So those who don't have this installed, this is a typo. It takes some time because it's on the cloud, but typically you have everything here, like boom, it creates the plots, and so you can use Colab for the most parts of the code. In fact, they also have MPI. I'm even running as root. Okay, that's good. Okay, anyway, let's go back to my Jupyter. So let's do some simple stuff. You create a notebook, and typically you would say like from NumPy or import NumPy as NP and so forth. But for simplicity, I will use this magic called PyLab inline. It loads already everything for me. So it loads matplotlib, it loads NumPy. It's not actually the best way of doing it. If you're doing production, you will never do it. But anyway, I have everything right now. NumPy is connected, and so forth. By the way, so what's cool about this interactive thing is that you can learn a lot by simply saying like A equals, for example, NumPy linspace. This linspace will create a linear space from 0 to 1 and let's say 1,000 elements. So this is now A is from 0 to 1, and it contains obviously 1,000 elements. But you can learn a lot from anything by simply saying A dot, because A now is an object, and objects have properties. And now you can do you guys hear me, others?
Yep.
Yes, we hear.
Okay, so I don't know. Are you in the breakout room? Yeah, something on your side, but you will have a recording later. But try to fix it. Okay, so you can learn a lot of the properties by simply putting A dot and then pressing tab, and tab gives you an idea of what's inside, what kind of things you can do with this. So for example, you can see, okay, like copy, conjugate. So obviously conjugate, you can, if it's a complex number, you can do conjugate, or dot product, or dtype. For example, we can find out what dtype is. Dtype is again an object. So an object means that we have to do this, and we find no. So boom, and it tells us that this is a float 64. What else is there? So put tab, and then for example argmax. It's a function. Okay, then you do it like this, and it tells you the index of the maximum element, right? So it's understandable. Argmax, argmin will give you the argument of the minimum element. So the way to learn fast is exactly doing this in Jupyter. Like if you don't know something, tab, boom. What else is here? Cumulative sum. So can you imagine what will happen? It's if A, for example, again, we can immediately plot this A. A is this is number of elements, 1,000, and this is from 0 to 1, right? And cumulative sum of A, it's an integral, essentially. Cumulative sum means you go, first element will be sum from 0 to 1, second element will be sum from 0 to 2, third element will be sum from 0 to 3, and so forth, right? So, and you see again, now you see a parabola. So this cumulative sum means essentially if you want to take an integral, then this is the way to do it. Okay, chat. I cannot send the link to the room because it's inside the who's on the side? Because it's inside the Zoom itself. Or guys, can you help out as well? Okay, so again, bottom line, A dot and then tab, and then you learn a lot. So now we created linspace, we can create functions. So for example, if we have, let's say, -10 to 10, 10,000, if this will be our x-axis, then we can create, for example, a Gaussian, like simply x squared divided by 10 squared, and we can plot this x and y, and this will be, x is not defined. Okay, run it. You run it by shift enter. This is called a cell, and you run the cell by shift enter, and simply typing is just enter. Shift enter will run it. Boom, and you plot your Gaussian. Let's put a bit more. Now you have a Gaussian. You can plot it immediately. What's next? Let's create a matrix. NumPy already has a lot of things for you. For example, if you have x equals this and y equals NumPy y, for example, like x squared. So you have two arrays, and now you can multiply those two arrays. What it will do, it will take and element-wise so element by element, it will multiplied 0 element of x by 0 element of y, and put it in the next next element, and so forth, right? You can also do dot product. And it will now calculate, I believe it will now calculate basically how it's called, the scalar product of two vectors. You can create matrices. For example, x equals zeros, np zeros, and then you put a size. For example, if you put x equals np zeros of 100 and put x, and this is just an array, one-dimensional array of 100 zeros. You can put here, let's say, ones. Now it's an array containing only ones. You can put a size here, like 100 by 100. Now it will be a two-dimensional matrix. See? So now it's a two-dimensional matrix of ones. You can create also a random matrix. You can create, I believe, how is it called, the unit matrix. And I don't remember how to do it. Igor, do you remember how to do a unit matrix?
You mean?
So once on the diagonal. Maybe diagonal. Yeah. 100, 100. No.
There is, yeah, np diag, yes.
And then I believe I have to put the size of it.
You have to. You have to plot np diag, then the array of values, and it will create.
Okay, so Pavel already showed npi, and then what? 10. There we go. So it's 10i. Okay.
Yeah, npi is identity matrix, and diag is more general type.
Right. Yeah. So and you can also plot them. So we have when I put plot, yeah, plot. Essentially it's PLT plot, because somewhere here we said from matplotlib, and again I can use tab for helping me finish it. Matplotlib.pyplot. No, import. Yeah, from matplotlib. Import matplotlib as PLT, I believe, something like this. And I can plot. I can also do two-dimensional images. So imp show x, and it shows me the plot of this, like a two-dimensional plot, where this is obviously 1 and this is obviously 0. I can play around here, like aspect equals auto. This will kind of create a more screen-fitting version of this. And I can say where the origin is. By definition, the origin, the 0, 0 is here, but I can put origin to lower, and now the origin is here. So sometimes very very important. Okay, now we can create a random matrix. So matrix A will be random matrix. We say numpy rand. So this is the library for random numbers. So you can have, again, put np random, and then you put dot and tab, and then you can again learn what's inside here. So a lot of things: exponential, normal distribution, Pareto distribution, Poisson distribution, random normal, again, just random from 0 to 1. So this will give you a number from 0 to 1. So A, C, and then, so this generates you a uniformly distributed number from 0 to 1. If you put M, this will be the, let's actually do it, x equals np random and like 10,000, and this is the number of random numbers to be generated. So now after this x will be in one-dimensional array of 10,000 elements with random numbers. Yeah, so this is and then we can plot it, and this is your random numbers. And you can also do the histogram.
It's better to plot, not.
Your connection is not good. So to plot what?
Sorry, yes, I meant histogram, exactly.
Yeah. So but if you want to see, this is the noise, and then if you want to see histogram, per definition, it will create a certain. Yeah, it creates the output. To quiet it, you put dot this semicolon, boom, And this creates a histogram. Per definition, it creates, I believe, 10 bins, but you can specify the number of bins, like let's say 100. And now it creates your histogram of the distribution, right? So if you put more here, it will be more smooth. And obviously, this is a Gaussian distribution, normal distribution. You can find all the properties of it and so forth. If we just put rand without n, this is uniformly distributed. So now if you create a histogram, it will create a uniformly distributed. See, the histogram is from 0 to 1 and more or less distributed like this. Yeah, histogram. You can, of course, create random, also two-dimensional. Like you put the shape here, like this, and this is not working. See, I already forgot. Why it should work actually? Like this. So X is now X. You can find the shape. Shape of X is 100 by 100. So now it's a matrix. We can see how it looks like in show X. It will be just random now, random plot like this. So zeros and random numbers. So nice way to generate random images. Tuple. So like this, you mean? No. But like, so it works like this. So two-dimensional image. And we can also, of course, create now the histogram. How do we actually address? So X, we can address 0. So everything, but from the 0, this is column, I believe, from 0 column. And we can plot the histogram like this of only a 0 column. So this full column means take all the elements, and this is like only the 0 element. And yeah, you can specify which like ranges, like from 10 to 20 elements, from 10 to 20 like this, or all elements, or 10 to 20, but take every second element like this, or like from everything. So -1 means the last element, -2 means the second to last, and so forth. Right. Or we can create a two-dimensional histogram. NumPy has this. NumPy has HP histogram 2D, and it takes values. It takes values. Hold on a second. We cannot do histogram 2D on this data. If we have, for example, imagine you have different particles, let's say distributed, NP random. So you have randomly distributed particles in some plane, pixels in the plane. So rand and 100,000 particles in X. So this is the X coordinate of the particle, and this is Y coordinate of the particle. And then we can plot NumPy histogram 2D and put XX, YY here. And actually H2 we don't need, but no, H2 we need. And we can show now H2. Why not?
Don't you need to create mesh grid from XX and YY?
No, I don't think so. But yesterday I did this. Why doesn't it work? So this is a histogram, obviously. So, okay. So see, Python helps you a lot. So when you look at it, it has something here. Like obviously, this is an array followed by some bin data and followed by another bin data. So obviously, if we put H2 here, H2 equals this, and then H2 has different properties. And we find out the properties again, putting dot and tab, count and index. Or we can say 0, what is there? Obviously, 0 element, again, H2, we can plot it and see. This is some kind of a list, or hold on a second, this is a tuple. And we can find element by element what's there. So obviously 0 element of this tuple is our data. So 0 element, boom, it just returns the array. First element is a one-dimensional array which tells you where the bins is allocated. So the limits of your bins in x direction, and this is the limits of your bins in y direction. So shift tab, yeah, of the function shift tab, you're right. So here, yeah, and we can learn a lot here. Bins, range, yeah, weights. But we can now plot H2, again, wrong, the data, and this is our distribution. See, if you had the particles distributed in some way, and then you plot, you create this histogram, which is a blob. Okay, now let's go back to the matrix. So we have now the matrix which is 100 by 100 randomly distributed, and we have y equals np random rand also 100 by 100. And let's do matrix multiplication actually by hand, because we want to learn for loops and so forth. Of course, NumPy has the product of matrices already. So for example, I believe if I say matrix it's a function like, but a equals x times y, this is already a result of the function. So it created again now the multiplication of two matrices. So NumPy already has matrix multiplication, so you simply do x multiplied by y. Is this true? Let's do matmul. And let's see if I'm correct. 0, 0, and b is equal to x times y. Print a 0, 0, print b 0, 0. Yeah, I was wrong. So matmul, yeah, element wise, exactly. Exactly, you're right, Ivan, you're right. So you can do like this, and this will be then exactly. Okay, thanks. So, but in principle, you can write either matmul x and y, b matmul like this, or element wise. So you element by element. So 0, 0 element multiplied by 0, 0 element. You write x multiplied y. Exactly. So this is element wise. This is obviously matmul, and this is matmul. Okay, now let's do the very stupid matrix multiplication to learn about for loops. So we have two matrices x and y, and then we want to find matrix z, which will be the result of matrix multiplication. And we now do the naive matrix multiplication. So remember, it's row by column, right? So for example, we start for I. The loops are done like this for I in, and then we also know the size of the matrix. So in n of rows equals 100. Actually, I'll put it here. N of rows equals hundreds, n of calls equals 100, and I'll do n of rows here, n of calls here, n of rows here, n of calls here. So there is a way, of course, to find out the size of the matrices, right? So we, for example, put x shape, and it returns us the shape. So obviously x shape 0 will return us the number of rows, and x shape 1 will return us the number of columns. So for example, we can do for loops for I in, and then we put our range of shape of x shape 0, and then it will return us, like for example, print e, it will return us numbers from 0 to 100, obviously. So, and this is the way to write for loops. So it goes for all i's in the range. A range is simply, if you put a range, let's actually put somewhere here, a range 10. It's from 0 to 9. It creates you an array, NumPy array from 0 to 9. Okay, so and because this can be iterated, so I will go from 0 through all the elements of the array. It can be also a string, I believe. So L equals hello, or string S equals hello, and I can put here for I in S. Okay. So, and S is a string, so a string is an array of chars, and it can also be iterated. So that's why when I put for I in S, it goes symbol by symbol, okay, and then it prints all this. If you want to find also the number of this, there's a cool feature called, like, if you put N and S, and then you say enumerate S, and then it returns both the number of iteration and the iteration itself, like this. Okay, so this is a cool way of going through the arrays. I'll take a look quickly in the. Good. Now let's do stupid matrix multiplication for I in arrange. Typically, if you write it, it's of course NumPy arrange X shape. Actually, let's put n of rows for j in np arrange. We assume that the matrix is. Let's assume for the simplicity that the matrix is square. Okay, and then for k in NumPy arrange n of rows as well, and then we have a separate matrix, and we have to allocate it first. So we say z equals NumPy zeros of size, again, size like this, n of rows and of columns. And so, and now data type not understood.
You have to provide a tuple, not two arguments. So you have to create a tuple from n of rows and of columns.
Mm-hmm. Actually, I better put the type as well. For if I'm really good, if I'm taking care of everything, so then I provide the type. D type equals np float 64. So then it creates basically matrix of zeros, n of rows, n of columns, and it assumes that every element, although every element is a zero, it can be an integer in principle, right? But I tell explicitly that the data will be floats, or for this sake, I can also use double, I believe. Yeah. And because here I had my random numbers, so this is obviously, if I ask, I can ask also a lot of information about my x and y. X, D type, float 64. And then we can ask np float 64. What is it even? It's certain, like it's a type, right? And then we can ask if it's equal to double. And it says true, right? So float 64 is the same as np double. On this particular machine, of course, this depends on the machine. If you run it on like 32-bit machine or like higher level machine, then np double is not necessarily equal to float 64. Okay. We can also probably ask for more. Float 64 is what? Is it type? And then we can ask, what do you have here? Like, what is even this? Okay, but you can ask how many, I think size is here. No, I should be able to ask how many bytes is that. And I believe somewhere here it is. Anyway, this bytes, maybe like this. I forgot, but anyway, you can Google for it. You can ask for the number of bytes inside this each type. Okay, so now we have matrices X and Y, and now we want to find the matrix product, and it's a good example just for the for loops, and then of course Z, and then you say Zij. So this element is equal to the row by column, right? So this equals Zij plus row A I like this, multiply by bkj. I think it's like this. So, and let's just run it. And it doesn't want to. Because this is x and y. So, and then z 0 0, and we have our matrix A. So I made a mistake somewhere, probably. No. Item size, okay. So let's try it. Item size. It is an attribute, so like this. No, doesn't work.
No. So once again, np.dtype, then type, np then you type type as argument of a dtype function, yes, and then attribute item size.
8 bytes. 4 bytes. np int 8 bytes. Okay. Okay, so we created a very naive matrix multiplication. What can we do with it? We can actually create much more. Where is our matrices here? Let's say 1,000 by 1,000. Still 10,000 by 10,000. See, now it takes some time to create. Takes some time to so this asterisk here means that it's running. So 10,000 by 10,000 is already taking some time. So it's too much. I can stop it. I can stop the kernel. Doesn't want to. Okay, so maybe like 2,000 by 2,000. Okay, it took some time. What can we do with it is the following. It's very cool. We can time it. We can calculate how much time is spent on this. So we can simply calculate x times y and calculate the amount of time spent. So it will do it for us. This is called magic. This is called line magic. So you put %, some comment, but %time it will give you the information. This is a good way to profile your codes. So now we can find out that this operation x matrix multiplication takes for NumPy, or somebody already wrote it for you, takes 85 milliseconds. And what it did also, it did 7 runs with 10 loops each. So it created also the mean and standard deviation of this number. So, but now we know that it takes roughly 85 milliseconds for running it in NumPy. We can also do it for our function. We can actually define a function, right? Define stupid matmul. It takes x and y, and we just simply put this here. Maybe we can also. Okay, we assume that we have square matrices, so we say shape 0, and here also x shape 0, so that we don't have to provide the. You can create a docstring. How is docstring is like this, I believe. You can create a description of your function. Stupid matrix multiplication. Assume square matrices. Don't ever multiply matrices this way. And now when you write stupid matmul, and you can again shift, you can press shift tab, and now it helps you, like all this docstring appears here. So when you write, you can use docstrings. But okay, let's try stupid matmul and xy, and it calculates something, and it will actually, we don't return anything. We should probably return something. So while it's running, we can change the function. We can say return z. And it already obviously takes a lot of time. even too much time. So maybe it's too much for our stupid matrix multiplication. Let's do 1000 by 1000. And my computer starts exploding. So, but this is, so what's the purpose of this example? You know how to write for loops. Sometimes you will write a code where you have these nested loops, and this is fine. But of course, NumPy provides libraries for you that do matrix multiplication like this, and of course, use these libraries because they are much faster. As I mentioned, NumPy is written in C, and actually, NumPy also uses multi-threading, C multi-threading. So it's much faster than Python. So of course, if you do it like this, see, it's still running. So we have to stop it. Maybe 1000 by 1000. I don't know if maybe it will be also too much. Let's do 5000 by 500 by 500. It's still, now it will time it. Takes some time because it runs many, many loops. But now it takes 1 millisecond like this. And if we do stupid matmul, see how much longer it is. Too much. See, they cannot even do this on Python. So you can use range, a range. It's just, I think it's more as a habit. I use a range. You can use range, of course, no problem.
A range creates array and the range creates generator. I think it's memory efficient to use a range.
A range or range? What is more memory?
A range, just the range. It's not hold on memory the whole array at the moment.
Okay, maybe. Okay, thanks. So this calculated time, it's almost a second to run the same thing that NumPy does in 20 microseconds, right? So 20.
Maybe we try with the range now, just for experiment.
Yeah, okay, let's do it. Like this.
NP range.
NP range or just range?
Oh, just range. I think it will work.
Okay, let's see.
But we may.
It's faster, yeah. Actually, see, we learned today how to make things faster. So instead of 860, I believe it's 660. So okay, we saved 1/4, 25%. Not bad. Okay, thanks. Good info. But compared to NumPy, you still get here 20 milliseconds, right? So 658 times e minus 3, so milliseconds divided by 20 microseconds minus 6. This is incredible. NumPy is 33,000 times faster. This is crazy. So don't ever use it. But we can do crazy things with this stupid matrix multiplication later on and speed it up almost to the speed of NumPy. But this is just an example of like for loops and example that use libraries. So let's do something else. Let's do something that is typically done when we learn parallel programming, is how to calculate pi. So we have, the idea is the following. You have a square 1 by 1. So let me just plot it actually. Why not? Okay. Why not? Okay, anyway, imagine that you have a square from 0 to 1, and then you start randomly putting numbers there, uniformly distributed, and then you can calculate how many points will be inside the quarter of the circle and how many points will be total, and then based on that you can find out the value of pi, right? So what we do is create x equals numpy random rand, like how many numbers. I don't know, like 2 to the power of 10. How much is that? It's 10, divisibility is 10 to 24. Let's do 14. Yeah, 2 to the power 14 numbers. X and Y, those are coordinates. And each of those numbers is distributed from 0 to 1. And now we can do, like, again, the non-Pythonic way. And we will do it non-Pythonic way. But those of you who know Python better, like, you can actually try to find a way to do it much better. But in principle, we go through all the numbers, and then we find out which numbers are smaller than actually, what we do is we'll try to find if x squared plus y squared less than 1 or not, right? So in principle, what we can do is the following. We can do it in the for loop. Let's quickly do it in the for loop. For n in range n, and then we say, and then we have a counter. This is how you would do it in C, but later on we will find another way. Of course, we can do kind of masks and then find calculate in a different way. And let's call this function def stupid pi. It takes x and y, and n is global. Okay, and then we say if n squared plus yn squared is less than 1, then counter equals counter plus 1, and then return counter. So and out of 1,600, so the total was 16,000, and out of this 12,000, like 13,000 were roughly inside the circle. So now we can calculate the ratio. So we can calculate this number divided by n, and now we can calculate the ratio between pi. So the quarter of the circle will be pi divided by 4. Right, the quarter of the circle with the radius 1, the surface is pi over 4. And so basically this is the same as pi over 4 divided by 1. 1 is the area of the square with the length of 1. So basically this means that if we multiply this by 4, then we get a pi. So if multiplied by 4, boom, see, we have a almost pi. And this now will depend on how many we put here, like this is too much. Because we have to put this now. Let's do it correctly. But it's still pretty fast. See, we get an approximation for pi. We can do it, of course, faster. We can now time it again. This is your tool for all of you Python people, especially running Jupyter Notebook. Time it, use it always to find out what is your bottleneck. So 66.5 milliseconds, sorry, and now we can do it another way. So of course we have X and Y, and we can do I believe the masks we can just simply say it like this: X squared plus Y squared less than 1, I believe, and it will return me an array of if this statement for every element, it will return me an array with if this was true for this particular point element wise or not true. And then I can simply calculate if, especially what we can do, there are different ways. We can sum up this array. So this is array, let's call it A again, and we can sum of array. I believe this will work. Yeah, because true is 1 and false is 0. So we can just sum up this array and be done with this. And let's create our def, let's say better pi. It takes X and Y and it does exactly this and it returns, actually we don't need to, it just return sum of this. Sum is essentially NumPy sum. And boom, and then we can time it, better pi XY. So it's much faster. So NumPy is much faster, 153 microseconds compared to the 66 milliseconds. So essentially, whenever you're doing loops, think if you have the alternative to do it with NumPy. Okay, let's try something from your assignments, namely this mapping, right? So we had a mapping xn plus 1 equals r times xn multiplied by 1 minus xn. So the way you do it is the following. You just say r equals, let's say 1. And then you say x equals zeros of size. I don't know how we go, for example, n of steps equals 100. We go, let's say 100 steps, zeros of n of steps. And then we say x0 will be our value. Let's put 0.5. And essentially, again, we can do it with the for loop. And then later on, you can find if you can do it without the for loop. We say for n in range 1 to n of steps. We go from 1 because we already have the 0 value. This is our initial value, right? And then we say that xn equals r multiplied by x n minus 1 multiplied by 1 minus xn minus 1. Boom. And then you can plot x and see how it y. Did I do something stupid? There. Yeah, I did something stupid. I kind of put the equilibrium value from the beginning. So if you don't put somehow 0.5 is the value to which it converges for this R. So but you can see now that it converges to pretty quickly. It converges to the value of 0.5. And if we start changing R, so for example R equals 1, it converges to a different value. It converges actually to 0. So it goes to 0. Below 1, it converges to 0. So the population gets extinct. And if we go to 4, boom, you see now it's something crazy out of the sudden. And you can find the bifurcation point. I believe it's around 2.4 as far as I remember. So now it starts to go like over a bit off. 2.5. No, 2.9. Yeah, so 2.9 is already close to bifurcation. Boom, you see, this is now for r equals 3, it starts oscillating. So if we zoom in somewhere like from xlim from 175 to 200. You zoom in, and if we plot it even like dots or like this, you see it goes like one step here, 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 and basically it converges to this. So this is exactly called the bifurcation. So before R approximately 3, you had a single value, so it converges it to the single value, and then after approximately 3, you have jumps. And now you can plot for every R. So basically what we can do is we can create a range from 0 to 4, let's say 100. And then for every R, we will now save like this last 200 steps. So we'll calculate for 400 steps, and then we will calculate the last 100 of those, for example. So we say def return last axis, and what it takes is R. Let's put the default value, and it takes x0, and yeah. So we say we run for 1,000 times. X0 equals x0, and you run it. And then you say, I want to return only x minus minus 100 to -1. I believe this will work. So I return only the certain, not because you remember our x, it had certain evolution, but we want to find out only what happens in the last 100 elements, let's say, and we want to plot them. So to create this bifurcation map. And yeah, so I want to return only one. It's 100. I believe it will be either 99 or 100. So now we will look. So now we will run it again. So for example, return last axis R equals 3, and x0 equals 0.2. Boom, and it returns an array, and we can ask for the shape. Tuple. Yeah, you're right. Yeah. -1 is the last. Yeah, okay, that's true. And this is an array. Why I want the shape of it? Like, yeah, it's now at 100. And now we can even plot this. You see, we can just plot it like this. And it returned that the last 100, right? Now we can change the R and see what happens. Like 2 will be the value. And now what we can do is the following. We can now create this bifurcation map. So we say, basically this is the part 1 of your assignment, but this is fine. This is for those who never did it. You can just like rewatch this and do it again yourself and do it better. So now we have an R is a range from 0 to 4, 100 steps. So R0 is 0, R1 is, see, I forgot how to operate with ranges. Can I even plot it? How do I access the R is obviously a range, so how do I access data or something? What's there?
Third argument, it's step. So you should choose small step, not 100. Ranges. So step, not like in linspace.
I got it. Yeah. I see. So point like 0.1. And the problem is float is going to be an integer. But this requires an integer. It requires an integer, so I have to kind of specify the amount of steps. Okay, so that means that I have to do it in a different way. I can specify the step. 0.1. Oops, I pressed something wrong. Yeah, but a range, we found out a range is stupid.
I didn't catch that. Could you try again?
I hate Siri. Anyway, we just found out that a range takes more, so you can speed up things with range. So we put step here, and then we find that our last value is R max is 4, and then number of steps will be obviously for R max divided by step, and we put it here. So we have equal. So we put here n of steps. Yeah. Okay. This will save a bit of time. But you see you can do it with the, so R equals numpy R range from 0 to 4 and 100. And now R is an what?
Maybe we'll just use linspace.
Yeah, linspace. Yeah. There we go. So it's a linspace, and now for every R we do this procedure. For every R we do this procedure. So we can also do either a for loop, or do it much better, maybe NumPy map. Those of you who know it, it's you can do it this way. So R for like RR in R. So first we create. Actually, we don't need to even create. So what I'm writing is not like perfect Python code, but this is just for you to see this mathematics. For RR in R, and so now for every R we do this thing. R equals RR and x0 x let it be 0.3, and this is x, and then we have to construct like so we know the shape of x. X equals 0. It will be the shape of length of R on one side, and on the other side we returned last 100. I mean, I don't hard code it here. I hard code it here, but later on you can fix it. So, and X shape is now 100 and 100, because length of R is also 100. Okay. Good. So now for RR in R, we return X, and then X, I believe here we can do enumerate. Oh, I'm sorry, not here. Like IRR in enumerate R, and then let's see if it works. Like this. It worked. So basically, for every R I save the last 100 and then just stack them together for every R. Now I have this information X, and then I can plot it in show. And basically, this is already a bifurcation map, because it started. So it started from again, this is the R axis. Longitudinal is an R axis, and this is the what axis? The last 100 of values of your map. And you see, for the beginning, in the beginning you had that your destination was 0, so your population was extinct and went to 0. Then it started growing, and here is the bifurcation, so it jumps between 2, 4, and then chaos. And you can also plot it the way I plot it, so we can probably just like do it in the following way. We can plot it here. So for every R we plot the following. What do we plot? Let's try it. And we want to plot this X. This will not what? This will not work right now, but I want to plot basically for every R, I want to plot the map. This obviously will not work. Must have the same dimension. So we put RR multiplied by once, and this is 100. This might work. So now we are seeing already something. So I want, I forgot how to plot it, but this is your homework basically, or your lab work, to plot the plot that I presented for you. So remember there was like kind of 0, and then it jumped, and then it started like going into 2. So it's something like this already, probably. Maybe like if I do it like this. Yeah, there we go. Black. So you already see the bifurcation. So it went like this. And of course you can do more steps in R, 2000. It will take a bit more time, but there you go, a bit cleaner bifurcation map. Okay, so I think we are out of time for today. I hope this helped. If you have questions, please ask. But in principle, you code like this. You can do much faster using NumPy, but in principle, especially if you know Numba, this will be fine. So, and we roughly did already your first assignment. So I'll close the room. So let's go back to the main room and see if there are questions. If you can ask there as well. So how do I close the room? So any questions or? Yeah, okay. So how do I close the breakout room? There. I close all rooms, so let's go back. Okay, guys, I think we are done for today. So I'll stop recording.